With America entangled in heated arguments over wars, budgets, healthcare reform, and the space shuttle's successor, a bold new course was required to unite people of all religions, ethnicities, and socioeconomic backgrounds. President Obama announced a new goal for NASA: to find out, with all possible speed, the effects of various gravities on the solidification of fluids and the formation of mushy layers. And so it was that the people of planet Earth turned to one elite group of young scientists for the fulfillment of all their dreams.
Good afternoon, my fellow Americans. I am Joe O'Rourke, president of the Yale Drop Team, Yale University's undergraduate reduced gravity research group. Charlie Bolden, the NASA administrator, has asked me to organize a group of undergraduates to spearhead NASA's bold new course. I have selected you because of your diverse background in science and engineering, but most of all, because of your enthusiasm for a research project that literally cannot be replicated on Earth. Successfully performing this experiment will require stellar writing skills, a great work ethic, and of course, extraordinary analytic prowess. As you know, failure is not an option. Any questions?
For teams not operating under executive order to perform the best experiment ever, is it difficult to apply to the Reduced Gravity Student Flight Opportunities Program?
If a group of undergraduates has an involved faculty advisor and a deep reservoir of enthusiasm, then writing the proposal becomes much easier. The program coordinators are always tremendously eager to answer any questions.
This sounds incredibly expensive. How do you afford to build your experiment and travel to Houston for Flight Week?
Yale University is a wealthy institution, but the majority of our funding comes from outside groups. Every state has an individual space grant consortium which offers numerous grants and fellowships. Plus, the ability to write successful funding applications is invaluable for graduate school and beyond.
So why again are we studying the solidification of fluids in various gravities?
Pearson, that's obviously classified. I can't tell you. But rest assured, I have thoroughly discussed the rationale with our faculty advisor, Professor John S. Wettliffer. So, Professor Wettliffer, what are the applications of this research?
Since at least calcolitic times, humanity has tried to control the solidification of partially molten alloys, but those processes are substantially compromised by gravity. So in the case of these experiments, one hopes to control the properties of the material by manipulating gravity. The applications have to do with trying to remove the deleterious effects of gravity, which influence the transport of fluids, which influence the solidification and dissolution of the end product.
Has anyone done anything like this before?
I don't think anyone has done these experiments before over the time period that they've been done. No one's grown a mushy layer for a period of hours in oscillating gravity. Some people have flown dendrites on the space shuttle and on the International Space Station to see the effects of gravity on single dendrites, but no one has studied this.
I'm incredibly envious of your Yale education and your good looks. Tell me how you're building the experiment or I will turn off all of these cameras.
No, we need the outage material. I'll tell you everything, but you'll never stop the team. They're much too talented.
The solution is contained in a custom-built plexiglass cell with a copper base. Placing the cell on a container of ice packs induces solidification from below. A projector is used as a light source, and data are collected with a commercial SLR camera. In conformance with NASA's stringent safety standards, the entire experiment is contained within the test article.
Having a good time. A shooting star leaping through the sky like a tiger, defying the laws of gravity. I'm a racing car
we see here?
The so-called mush layer is at the bottom. Instead of solidifying as a solid crystal, salt dendrites crystallize from the unstable solid-liquid interface. These undulating channels are freshwater plumes. Fluid left in between the mushy layer's dendrites is convectively unstable in normal gravity because it is less dense than the overlying salt water.
Look at this video from one microgravity parabola. Convection stops and the plumes disappear because buoyancy is no longer a force.
And in hypergravity, the plumes come back much stronger. In this video, you can see exotic phenomena like coupled oscillations and Rayleigh-Taylor instabilities in a jet.
Wow, we should submit these results to a peer-reviewed journal for publication.
Yeah.
Sounds good.
Oh, hey!
Joe,
Joe!
how'd you break free?
It was only Harvard.
Ready or not, here comes science. They might be trying to